Assalamualaikum and hi. My name is Muhammad Iqmal Firdaus bin Muhammad Razapi, and today I will talk about the optimization of instrument condition for the analysis of mercury, arsenic, antimony, and selenium by atomic absorption spectroscopy. So, the main topic discusses what we are going to do with it. So, the technique used is cold vapor generation atomic absorption spectroscopy and hydride generation atomic absorption spectroscopy. It will optimizing instrument parameter, helps to improving the sensitivity and reliability of the result. Optimizing also reduce interference from the species which may trying to compete with the analyte of interest for hydride formation. It's for HGAS. And the parameter optimized, there are four. They are reagent, sample and argon fluoride, acetylene OA ratio, concentration of reagent, and the delay time. Hydride generation atomic absorption spectroscopy is used to detect arsenic, antimony, and selenium. So, let's go to hydride generation AAS, atomic absorption spectroscopy. So HGAS, its use separation of analyte from matrix by a conversion to the volatile hydrides. Then second, it is excellent low level of detection, and lastly, it the sensitivity at wavelength below to 200 nanometer, whereby a region where there is considerable spectral interference from radicals in conventional flame AAS, atomic absorption spectroscopy. There are three distinct processes for the HGAS or hydride generation atomic absorption spectroscopy, that is hydride generation and release of the element of interest from the sample solution with the aid of a reducing agent. Second, hydride collection, and third, the atomization. So that we know that there are factors that will influence the yield on the hydride generation atomic absorption spectroscopy AAS. The first factors is concentration of acids, and second one is concentration and types of reducing agent. Number 3 is fluoride consists of 3 carrier gas, reducing agent, and gas. And number 4, rate delay time of sample. So, how we detect the mercury one? The mercury one will use the cold vapor atomic absorption spectroscopy because it is the most sensitive method for the mercury determination. So, there are also principle of cold vapor atomic absorption spectroscopy techniques that are: number 1, the reducing agent typically used that are stannous chloride, CnCl2, used to convert ionic metal ions of mercury 2+ in aqueous solution into Hg0 or mercury no charge, which produce higher analytical absorbance signal. Number 2, high vapor pressure of mercury is liberated and entrained in argon after passing separator. Later I will discuss in the the procedure. Number 3, mercury vapor transferred into optical path of AAS, where mercury absorbs light of specific wavelength at room temperature. And lastly, the sensitivity and precision maximized through the optimizing of parameters. There are 3 of it. So, number 1, concentration of reducing agent. Number 2, the fluoride of 3 reducing agent, that is SnCl2. Number 2, the sample. And number 3, the purge gas. And lastly, the read delay time. So, in the diagram above, it is a schematic diagram sketching of how the procedure of optimization of parameters occurs for HGAAS and CVAAS. So, these are the procedure above. They are, from me, there are 10 steps that can be used and into a very easy point. First, there are 3 calibration standard. There are 10, 30, 50 ppb of calibration standard were prepared for each metal that will be analyzed in 50 ml of Erlenmeyer flask. Number 2, the mercury will be optimized. Number 3, the concentration of reducing agent varied and acid solution were prepared in volumetric flasks. Number 4, the respective solution was placed in a 25 milliliter measuring cylinder. Number 5, volume of reagent used in the 60-second were determined by the flow rate. Number 6, adjustment knob either tighten or release. Number 7, the ionized water pumped through the entire system for 60 seconds while being analyzed. Number 8, varying the pump tubing internal diameter. Number 9, absorbance for sample were recorded each change in flow rate of acetylene gas and argon. And lastly, temperature of a acetylene flame was optimized for the atomic absorption spectroscopy by regulating the flow rate of the acetylene gas to oxidant. That's all from me. Thank you.